Chemistry in Society. This is lecture chapter 10, polymers. And speaking, Tania Cordova Santiago. This is the topics outline. We're going to here in this chapter learn about polymers, what is a polymer and a monomer. Natural polymers and what are chemically modified. We're going to see the structures of the main types of polyethylene, learn about the concept of something that is a polymer thermoplastic or thermosetting and how that depends on the polymer structure. Identify the monomer in an addition polymer, cross-linking and polymer properties, addition and condensation, polymerization, the structure of monomers that form polyesters and polyamides. What is the glass transition temperature? Crystallinity, what is the effects on the physical properties of polymer, environmental polymers, problems associated with plastic and plasticizers. So critical the environmental issues these days with plastics. Then sustainable non-petroleum-derived polymers, their sources, and be able to explain how life cycle impacts the environment, benefits of newly designed products, new polymers. Okay, so first was a polymer. So polymer is a very large molecule, macromolecules, and they are made from small molecules, which are called the monomers, the parts. So here is that what I have here is like a polymer made of Legos. So each of the little bricks will be the monomer, and the whole structure is a polymer. And what we have below is a polymer, and we see here a long chain of carbon and hydrogen. So, but that's essentially the small parts that make the polymer are called the monomers. There are natural polymers, and we have, for example, a starch in cotton is cellulose. Another type of, say, structurally somewhat different is cellulose in wood, and also proteins. Proteins are polymers made of amino acids, and they are constituent um, many things in our body and made of amino acids, or protein containing amino acids. And also a huge, very important type of polymer is actually DNA, RNA. But these are the natural polymers. So substances are very large and that are made of monomers. Now, this chapter is more about non-naturally occurring polymers, but rather those that are synthesized. Now, the industry of polymer is started actually from modifying an existing polymer, a natural polymer. Industrial cellulose was produced, the first polymer. So it was made by treating natural cellulose with nitric acid. And again, that's one of the earliest. And, at the beginning, for example, the balls used for billiard uh, uh, were made of ivory from elements. So you can imagine that practice is not at all good for the elephants. And so this replacing the balls with the material, the celluloid, was a great step, even for conservation of that species. And also, we have another example of use of celluloid, which is the films. Back in the day, that's why we call the film industry the celluloid industry, because the first movies were made out of that material. Now, here is one very common polymer. That's polyethylene, and we see there's a long chain that made up actually the plastic. There are many forms of that, but the more one of the first one, the more the simpler one and most common is polyethylene. So how is made of polyethylene? There are several types, and here we have what we call high density polyethylene, so HDPE, and these are linear molecules, such as the figure that we saw in the previous example. So the monomers are closely packed together, and because of that, it becomes more dense. So this is what we use in milk jugs bottle caps, toys. Now there is another type of polyethylene, and this is called the low density polyethylene LDPE, and this is obtained from more branched monomers. So here, for example, in the high density polyethylene, the monomers are just ethylene units, so it's not branched out, and so molecules are packed together. But if we use this is actually a copolymer, so made of two different type of monomers. So ethylene and this one that is branched out, so 4-methyl 1-pentene, these two units made a new polymer that's called the low density polyethylene. And the fact that it's lower density is because this is branching out. It does not allow the tight packing. So you can visualize it as these two different type of Legos together. Now, you cannot have two chains very close together. And that's what makes it the low density. That's the plastic that we use for plastic bags, plastic films, water insulation, and so on. So here is an example of polyethylene. Now, when you heat up this two type of polymers, so the high density and DPE and the low density polyethylene, they have different properties when they are heated up. So the one here we have two bottles. One really say that you heat it at the same time, and one kept its shape and the other is deformed. So that's a big difference between the two polymers. So the high density, because it's tightly packed, conserves the shape, whereas the low density is it looks like melted, so it is deformed. Now, this leads us to a couple definitions. So thermoplastic and thermosetting polymers. So thermoplastic are, as the name said, plasticity, so they change form, so they soften upon heating. So polyethylene, the low density, is particularly um, thermoplastic properties because it can is soften and change the shape when it's heated up. Now thermosetting polymers, they are actually they they will not soften essentially when heated up. But they may discolor or decompose, but essentially they're not soft. They will not deform upon heating. Now we have type of polymer here. In essentially what happened is an addition reaction in the polymer, so we're adding monomers together. That's why we call that as addition polymerization. And so this is polypropylene, so made up units such as this one on the right. In the monomer you have a double bond here, but it's three carbon atoms. So these here is several repeated units. That's why you have here the structure in the brackets, the three carbons and the N molecules. So these are formed in addition reactions. Now polystyrene is made of this molecule. So styrene is vinyl benzene. So this is the molecule that we see here on the right. And notice in polystyrene, we have this unit being repeated. But notice one important difference is that in the monomer, you have a carbon-carbon double bond, and this is not anymore in the polymer. So the addition reaction had occurred, putting these monomers together, and in the process you have changed this double bond to a single bond. So but these are N units. So in the polystyrene has a number of applications. One of them is being in the insulation materials. Now here we have PVC, very common material. This is polyvinyl chloride. So in the monomer, we will have a double bond here between the two carbons, not in the polymer when these units are repeated. So polyvinyl chloride, that's why we have the C here. So many units of that in this can be molded into many things. So here you have pipes. This is ceilings, Some insulation materials. Here you have one more. This is fabric that is used to for raincoats and things like that. Now, other type of adhesion polymer. This is tetrafluoroethylene. The the tetrafluoroethylene, that is Teflon. And so we will have the monomer. Let me write it down. So the monomer will be carbon and carbon, and we will have four fluorine. So that's why we call that tetrafluoroethylene. So the monomers. But notice that each of the carbon it has is bonded to two fluorine atoms. So that's the structure, as I said, that monomer. When we put those together, again, it's important to remember that the double bond here in ethylene is no longer in the polymer structure. You replace it like you are adding several of these units of this monomer, and in the process you lose this double bond and you make new carbon-carbon bonds. And this is what we have in the pan. So a non-sticky surface is Teflon, which is polytetrafluoroethylene. These are some examples again of some addition polymers. And what is a monomer? As I was saying, here you have ethylene. So polyethylene, we have several of those units. And again, notice double bond here, not a double bond in the polymer. That is replaced this new bond by um, joining two other monomers together. You lose that double bond, you make a new carbon-carbon single bond. So the uses of polyethylene, bags, bottle toys, electrical insulation. Now here you have polypropylene. That unit is propene. This is propene, and so or propylene. And these units repeated again. Notice when you're making new carbon-carbon bonds in a polymer, you're losing this double bond here. But this is a unit that repeats and it has three carbons. So polypropylene in carpeting, bottles, luggage, etc. This is polystyrene, so that's the styrene. Again, double bond here disappears in the monomer when you put in this these units together. And now you have here the letter N saying that you're repeating these linkages n times. So polystyrene, and you have that in furniture, isolation, installation material, cups, toys, packing, etc. Here's more of these. So PVC, here, PVC, and again, you will have um, this is vinyl chloride. This is structure, vinyl chloride. Now we have poly vinyl chloride again, replacing pi bond is no longer here, and you're repeating this unit with two carbons and a chloride. You're repeating that n times, and PVC in pipes and a lot of things. And now this is um, vinyl chloride. So this is here you are is similar to ethane or ethylene in the sense that we have ethylene will be CH2 double bond CH2, and here in this particular monomer you have replaced two in one of the carbon the two H's that are bonded, and you're replacing that by chlorine atoms. So that's the change here. And you are now, again, you're losing the double bond when you're repeating this unit. This is Teflon, so remember, use several, so polymer. Several units, so tetrafluoroethylene, so again, this unit from two fluorine atoms attached to each carbon. So that n times losing the pi bonds, you make Teflon in cooking utensils. And here is the polyacrylonitrile in this. So this carbon nitrogen triple bond is what we have here abbreviated So this is not affected in the polymerization. What you're losing is actually the pi bond when you're making these unions and repeated unions. Alright, so more polymers here. Polyvinyl acetate in adhesive, textile coating, chewing gum, resin paints. And so here again, this group here, this is the ester linkage. This is in all of the units. So this is not touched in the polymerization reaction, the ester unit. What you're changing is the addition reaction happens using this pi electrons in this bond. This is us, and forming this lone change. Replacing again pi bond by new carbon-carbon bond. Same thing happens here in polymethyl methacrylate. This unit has an ester functional group again. This is two ways of um, writing the same thing, the same ester group. And again, you are in the addition reaction now. No longer pi bond here, and you have new carbon-carbon bond. So more and more things. Now some polymers are able to conduct electricity, and those are made by the same type of reaction, addition polymers, and polyethylene has many conjugated double bonds here. And it actually, when you have this um, many double bonds like that, there is remember these are pi bonds. So these electrons are more loosely bonded together. So these are special and they can conduct electricity due to the fact that these are the pi bonds are weaker bonds. And here you have extended, what we call extended conjugation. And so these are great to conduct electricity. Now, we know that some plastic, when temperature is increased, they can be melted and we can make polymers with different shapes. So plastic materials that can be modified under heat, they're thermoplastic, as we saw before, and you can make molds and make different shapes. So under heat and pressure, you can do that. So there are several processes to do this various products. So we have compression molding. So we use pressure, and this is here. Say this apparatus is pressing this on top of the say this polymer substance. It makes a shape, and that way you can make a lot of these. Another method is to do an injection molding. So plastic is melted and you put it as pores into cold molds. All of these methods is to make these different shapes for utensils that we use made out of plastic. Other ways of molding plastic is extrusion molding. So molten polymer is extruded through dye and continued form to make coils. You can make like a long coil, a thread, and make with that even fabric. Blow molding is something similar to what is done. This is to make bottles essentially. You blow in and make this, as we have here, blowing air in those polymers. So here the polymer substance is the blue one. So when you do that, you can make bottles out of plastic. This is similar to the process actually blowing um, glass. And we can make glass bottles in a similar way by blowing. So blowing molding. Now there are other polymers. Very useful. The rubber and other elastomers. So they, as the name says, they are elastic. A lot of plasticity. And here we have a number of things that can be made by that. This is isoprene. And here notice that we have two double bond, but polymerization you are now replacing now, we're making a new pi bond in polymerization. The product still has one pi bond. You have all these units being repeated, and that is rubber, only isoprene. We say it's an elastomer because it is elastic. it changes shape, can change. So natural rubber is made of isoprene units. This is the structure of rubber. And below are some products like that. So rubber can be modified in a process that is called vulcanization, and that was discovered by Charles Goodyear, and this what is used to make tires. And when you do that, so rubber is soft, but when you make it react and create this sulfur cross links, so these are bonds that contain sulfur atoms. See this unit here. When that is included in the structure, that makes the rubber stiff. Somehow it makes it harder, and that's the vulcanization process that we use to make tires. And these are examples of that. So synthetic rubber is similar to polyisoprene, but again, remember these vulcanized rubber, if we add the sulfur bonds, uh, and we make this harder. So natural rubber is the polyisoprene, and this is obtained in resins from plants. We can do that from pines, for example. And this will be synthetic rubber, similar to that. This is polybutadiene, and that is an example again of a product from vulcanized rubber. Now another interesting material, this is another synthetic rubber, neoprene. This is using the scuba diver, uh, um, the outfit that they use to protect them from the cold. So this is very flexible material, resistant to oil and gasoline. So it's used to make a lot of things. And notice this is it's similar to polybutadiene, but it contains a chlorine here, and that was make this special properties of neoprene. Another synthetic rubber is a styrene butadiene rubber, and again, this is another example of a copolymer. And here, remember that when we see this word copolymer, it refers to polymer made up of two different units. Here you have a butadiene unit, this with four carbons, and this comes from the styrene unit. Here's another butadiene unit, plus four, and so on. So two different types of monomer. And so, but notice that we have 25% of styrene, so we have more bonds with butadiene. So notice here this unit is repeated. So that's the proportion to make this particular rubber, styrene butadiene rubber. And here we have a lot of polymers in paints using binders in paint. So again, elastomeric, elastic, remember? Binders. So that makes the paint more resistant to cracking, binds together. And also latex paints use such a product. These paints actually useful because the water is a solvent, and this is more environmental friendly. But here we have more example of polymer. These are condensation polymers. And so here we have condensation polymers are made up of a small molecules such as water, alcohol, ammonia. This is HCl. And so and this is how nylon, which is a polyamide. So here this see one amide bond instead. So in general, when to recognize a functional group, an amide is say this is a carbon chain. An amide will contain a carbonyl group, a carbon oxygen double bond, and here you will have an amide with no substitution of an oxygen. That's the general structure of an amide. So notice that when you form such nylon, the polyamide, you will have several of these units. And so this is the monomer. And you have several units. So, and you can make polyamide, you can make fabrics because you can make this long threads, you can make all of that and make, say, ropes, fabrics, anything from that. And here we have more condensation polymers that are used to make fabrics again. And here's some examples in here, your sneakers, your winter clothes, a lot of that. This polyester is a very common fabric, synthetic fabric. It's made by the condensation of molecules of alcohol in carboxylic acid. So here ethylene glycol, notice that it has glycols are compound that has two OHs. So ethylene glycol is that, and here you have pyridylic acid. So this is the carboxylic acid, and when acids in an alcohol react, they make an ester. And so this is reviewing what is from our organic chemistry chapter, the general formula for an ester is, say, we will have a carbon oxygen double bond, and we will have here single bond to oxygen and some carbon chain. And here I am going to say just R prime. But we call that condensation product. So the alcohol part reacting with the carboxylic acid make ester group, and this is an ester group. So notice this here this O, this part. Let me make that in a different color. This O and this H2, this is coming from this from the alcohol part, and this is coming from the acid part, and that's ester. So polyester, hence the name, right? So many ester linkages, so it's a polyester. Here we have another interesting condensation polymer, and that is um, bakelite, bakelite. Not sure about the pronunciation. Sorry about that. So, in this is the all phones were made of that. And this is a very stiff polymer. Those were very heavy foams. Now we use those, or they were used more in the past actually. This material is being replaced somehow. But it's a phenol, this is phenol and formaldehyde. So you will make this in many of those units will make this polymer in. So the first synthetic polymer, notice the patent is from 1909. And very old forms were made out of that. So now more condensation polymers. Here is melamine, and this is a lot of still plastic um, melamine, say thinner plates and stuff like that. This is for kitchen countertops are also made out of that. So these are uh, urea formaldehyde resins, and this is the structure. The one single monomer, and here you have two of these units together. So more materials, more useful materials used from condensation polymers. So here's phosgene condensating with uh, bisphenol. Again, we can say these are also copolymers because you have one type of monomer and another type of monomer condensing into one thing. So that is a polycarbonate. And that is the structural unit that identifies a carbonate. For example, and I'm going to do here the structure of carbonic acid. Carbonic acid is this here you will have OH and we're gonna have an OH here too. Oh, okay, so the molecular formula of carbonic acid is H2C, only one carbon, and 3 oxygen, CO3. I need to throw a number 3 here. And then a number 2. Okay. So that's carbonic acid. But what's important, this part is the same, see? And this is how we recognize that this is a polycarbonate. That's a carbonate unit. And see all these ceilings and all of that structure. Very nice to make, like window type. You make translucent things. Here's some more condensation polymers. Polyurethanes. Similar to nylon, you can make threads, you can make fabrics also as well. But here, roller skates used to have this material. In raw skate wheels, foam rubber, and furniture finishes with that. Here's something very popular, I would say, nowadays in doing fixing furniture. It is using an epoxy, the resin, and color dyes to make really nice artistic things. So you can have a wood and do some painting and then color that with this epoxy resin that is made of two different liquids. They combine and adheres to the surface and then becomes like a very clean reflective surface, really hard. And so it's very nice to make decoration. I have even seen floors made out of that. Beautiful. So it's popular nowadays in restoring furnitures and even floors. Composite materials uh, uh, fabrics, say fibers of high strength used to make ceramic tiles, graphite, fiberglass. And so tennis rackets, automobile panels, fishing rods made out of that. Here we have silicones. We have a number of these nowadays in kitchen because you can even bake on those. And so they resist the temperatures without being deformed, which is great. So we have newer tires that we adjusted for bicycles and things, but they have great properties. So polymers with silicone, in instance, in your periodic table, if you see the group where carbon is right under carbon is silicon. So in these polymers, instead of having a lot of carbon, they have silicon. So replacing that element. So very nice properties in this materials, as you can see. Uh, Now, okay. So polymers, we know these are made by a lot of monomers. So you then can point things with very long chain. Let's say zero carbon chain. So we can, in the high density polyethylene, we will have things like that, very close together, very tightly packed, and resistant to temperature in the low density we're branched out. But polymers are great. You can make strong fibers and you can make a lot of things. But in general, they have very high molecular weights. So because they're a number of atoms, a lot. And so they can exist in several forms, as fiber, as viscous liquids, hard things. So there are several interesting properties in polymers. Crystalline properties. They can make things that are very strong and very rigid. You can make things like for windows and things like that, but made out of polymers, not out of synthetic polymers. The one example that we saw before, non-glass containing exactly. And there are some amorphous. Amorphous is no particular shape, so these are random, not organized. This is more in soft polymers such as rubber, because these branches actually prevent them from being organized like that. So the branching out actually makes more these organized polymers more flexible polymers, whereas when there's so much branching, they tend to be more stiff. And so here there is another interesting concept, which is the glass transition temperature, and this is a temperature at which you change the properties about that from something that is tough and rubbery and becomes hard. So that's the temperature when that transition occurs from rubbery below that temperature to very hard, such the glass. So these is two examples. So that at the temperature at which that transition occurs is what we call the glass transition temperature. Here's some of the properties of fibers. Remember that we saw the polyester. You can make or polyamides. You can make fabrics, and because of that, you can make a lot of even synthetic clothes and materials. And in many ways, some of those are superior to natural fibers because of their resistance and durability. But that resistance and durability also makes it a problem because they are so very hard to decompose. And because of that, they have become a problem in the environmentally because they're not um, biodegradable, so they tend to accumulate in landfills and in water. So they're huge contaminants. So it is a problem. So polymers are being great in our say style of life. We produce a number of products that we're very used to in our daily lives. But if we don't deal with this problem, then we are going to be accumulating unwanted plastic. And so we need to think of ways of new polymers to prevent these contaminations. So landfills, plastic is a lot of that waste. So there is materials that can be incinerated, but there's no much value in that as a fuel. So they tend to produce a lot of toxic gases. So that is a big problem environmentally. So there are some biodegradable plastic, but not very many. So here is the opportunity for a lot of research for chemists to develop new and better materials, having the characteristic of all the plastic or the polymers that we want, but being more degradable. So work for the future. For now, is a good idea to recycle plastic. So some of the plastic in their codes for that can be recovered and melted again and given shapes and reutilized. So those recycling, reusing things one more than one time, so no single-use plastic. So reuse it a number of times. Or recycling is melting and that converting it to something else. But that is still limited, so we need to do our part and contribute to the recycling and reusing process. Another thing that is important to keep in mind with plastic is that plastic pose also a fire hazard. They're flammable, and there is, fires that can be terrible. Even communities like fires for a lot of houses, and they release fumes that are toxic. Oh, it's terrible. And so there is another substance that can be as bad as pollution agent because certain plastic, such as the vinyl polymers, we use plasticizers to make them more flexible because they're stiff. So we add these plasticizers, and these are here propylene glycol, oleic acid, but these are also a problem because these are small molecules and they are more volatile, so they can vaporize and become also a problem for the fumes. So here, early plasticizers, again, plasticizers is that substance to make the plastic more flexible when they're stiff and brittle. So we have, these are some of the early plasticizers, so polychlorinated biphenyls. And so biphenyl is this unit to rings together like that. So in polychlorinated, there's so many chlorine atoms. These are several types. That's why they have this different formula. And here's Daisy too. And so in more of that, recently we have some plasticizers that are less toxic, having less chlorine. So from phthalic acid. So these are, remember this functional group, this is carboxylic acid. So the phthalic acid in this are, we make esters out of that. So that's the unit, that's ester, where this can be any carbon chain. There are. So esters, phthalate esters, so from phthalic acid. And those are the newer plasticizers. So in the future, we have a lot of work to do because it is hard to imagine all the things that we have with plastic or things that are convenience, and they are part of our daily lives. But we need to be replacing these materials for new materials that are actually biodegradable and not have such a terrible impact on the environment. As the current ones, we have many that are a derivative from petroleum and coal. So that's not a good idea because not if they're not biodegradable, but many of them, there's investigation in having this that are similar to natural cellulose. So these are newer type of polymers. There's research about using making plastic bags out of materials similar to cellulose from plants, and so but modified to make them harder. So that's our future. So we will try to make materials to have the convenience of the things we want to have, but have no much less impact in the environment. But it is on us to recycle, to reuse as much as we can, avoid single-use plastic, and contribute to do or the environment to have our behavior and habits, say, as consumers, to be more um, aware of that and for a sustainable future.